Okay, so today's session is a revision session for for quiz 2. And so this session is probably a kind of doubt. Whatever doubts you have, we can discuss. Maybe there would be a next revision session. I'll ask to Mayur, he'll confirm. In starting was you're discussing, so probably maybe on Saturday we'll check it. That it may be on Saturday. So that day we'll discuss mock probably. So first let me know if you have any doubt, any kind of doubt you can ask. You can discuss that. Then we'll think that what we can do.
Sir,
Yes.
so can you discuss the properties of Hermitian and unitary matrix and how to calculate unitary matrix?
Okay.
That doubt I have.
How to calculate?
I mean, from a set of, matrices, how to check if a matrix is unitary matrix or not?
Okay.
Using the properties of unitary matrix.
Mm-hmm. Okay. Yeah. So the for quiz 2, important topics are so like knowing to be the properties of Hermitian and unitary matrix, uh, and then is diagonalization. Diagonalization diagonalization is going to be an important session. You should to know at least when a matrix going to be diagonalized or not. At least you have to be confirmed, and then once it will be diagonalized, you should to able to calculate diagonal matrix and the p matrix that would be the or even we can say the eigen matrix in different word. I hope you know that what I mean to say. And then next is yeah, surely positive definiteness would be there, checking when a matrix or sorry when a function is going to be or when a matrix is going to be positive definite, probably when a matrix. And next is in week 7. In week 7, PCA. Yeah, PCA is an important we have discussed in detail in last session. On PCA, probably the question would be, on the properties of PCA there. And in week 8, unconstrained optimization, that is nothing but finding, uh, critical points and finding the maxima minima. And gradient descent algorithm would be there one.
Can you mute everyone?
Sorry. Okay, so somebody is. Okay, let me present my screen.
So can you mute everyone?
Let me mute him. Okay, so in quiz 2 topics or knowing to be Hermitian matrix. Hermitian, the second is unitary matrix, and diagonalization. And next is SVD is also there in this week, I think. Sorry, in this quiz. Is singular value decomposition and positive definiteness. SVD is there. Positive definiteness. And the next is PCA is there. And after PCA, maxima minima, that is unconstrained optimization problem. And gradient descent. These are the topics, roughly 8 topics are there. So this Hermitian matrix is when we studied, the symmetric matrix, that is, we are going to, if we are the matrix in the complex matrix, then we call matrix. If the matrix is complex matrix, what is a complex matrix? Is that entries are complex number, and if that matrix, if a complex matrix have property that if we take the transpose and conjugate transpose of it. So let me confirm one thing maybe there we have seen the Hermitian matrix as here in the lecture star. Maybe it could be the same H is the meaning. If you see in QP, that is the same meaning. H and star are the same. You don't be confused with this. I hope, I think meaning would be written also probably. If not, but you will be understand what is the meaning as H is Hermitian.
What is AH?
H is in power of H is Hermitian. This is calling a matrix A is Hermitian. Sorry, here is taking the conjugate transpose. AH means here we are taking conjugate transpose. Okay, so and so matrix. Sorry.
A star will be conjugate transpose, right?
Yeah, both are. So that's the meaning. That is what I'm saying. If it is written a star or a H, you can think it as the same. If it is a star or a H, means it is the same.
We haven't used H in our lectures.
Yeah, everywhere. Yeah, I think everywhere is a
Star
star.
is
Okay, let's see that. If it is there, we'll see it. Okay.
Sir, in
But
general,
the
we have
meaning.
used complement transpose for star.
Yes, conjugate and transpose both
Yeah, for star.
for a star. Okay, we'll see it. That this translation will not be any problem here, but the meaning of AH is nothing but the transpose and and the conjugate or in conjugate and transpose, same meanings there. Okay, so unit. So this is the matrix is said to be Hermitian, means when AH is equal to A or A star is equal to A. So the means conjugate transpose are going to be same. Then we'll say the Hermitian, that matrix is Hermitian matrix, and it have some property. Hermitian matrix have some property. It have the eigenvalues. The main important property is eigenvalues are going to be same. Sorry, eigenvalues are going to be real. And the another property is if suppose not only real, the another thing is that if eigenvalues are going to be different, okay, means not if for the different eigenvalues, eigenvectors are going to be orthogonal. That is the property of of Hermitian matrix. For even you can do for the symmetric also, the eigenvectors are going to be orthogonal. Suppose for the case is that you have a matrix of 3 cross 3 matrix, okay, 3 cross 3 in which two eigenvalues are 5 5 and next is 3. So if you found, suppose you are able to calculate the eigenvectors for both 5 you separately, like let's say v1 and v2, and next is v3. So in this case, v1 and v2 are not going to be perpendicular to each other, means orthogonal. But it's sure that, so but not going to be, but it gives the surety that v1 is orthogonal to v3 and also v2 is orthogonal to v3. This should be there, but this may not be. Not even,
For same,
not even in, sorry.
sorry, for same eigenvalues, won't the vectors be similar?
Not there is no similar. Similar is
I
not
mean,
meaning orthogonal.
orthogonal, no, no, V1 and V2, sorry, lambda 1, lambda 2 are 5, so V1 and V2 can be same, right? Same
No, no, not
eigenvectors.
necessary. No, no, not
Not
necessary.
necessary.
If you are able to calculate two different eigenvector, that is fine.
Okay.
And all it is going to be always, because Hermitian matrix is always diagonalizable. Another property is that it is always diagonalizable. So you will get always for 5 5 you will get two different eigenvector, different in the sense of independent eigenvector. So these three are going to be independent. There is no uh, no dependency between these three. But we'll talk about the orthogonality. So for the same eigenvalue, the eigenvectors are not going to be orthogonal, but for the different eigenvalue, orthogonal are going to be, sorry, eigenvectors are going to be orthogonal. So this should be, so all of you please make this note. This is true. This is a property of Hermitian matrix.
And sir, all eigenvalues are real, right? For Hermitian.
Eigenvalues are going to be real.
So you've written the second one being eigenvalues are different, but you've also said that two eigenvalues can be the same, right? For an Hermitian matrix.
Not same. Different means independent, and they are
Okay.
not going to be same. So same meaning is not there. Means independent, and you will always get two different for the same eigenvalue. So okay, for the same eigenvalue, you will get independent eigenvector.
Okay.
Means
Okay.
here, as here you are getting, if the 5 5 are going to be same, then you are getting right two different eigenvector. You will able to get two different means, sorry, independent eigenvector.
Okay. So,
Independent eigenvector will get, but the orthogonality will not be there between them. Orthogonality will happen only for the different eigenvalue, means yeah, different eigenvalue, like for between the 5 and 3, their eigenvalues are 2 and 3, or even v1 also. Okay, this v1 v2 and v3, there v1 and v2 are the for the 5 and v3 is for with 3. So here we can see it, if they are different eigenvalues, if they are from different eigenvalue, then they are orthogonal. So this is a property for Hermitian matrix. Okay, this is an one important property. Many question, if you check previous grade type of QPs, you will see it. At least one option would be there on based on this. So this is one important property of Hermitian matrix. Next is unitary matrix we have. So unitary matrix is if you do A star means AH or A star. If it is if you do A star and then multiplying with A, it will be identity. Just a second. So if it is this one is happening, then it is going to be then we'll say matrix A is a unitary matrix, and other properties is that eigenvalues are going to be, I think, so yeah, regarding the eigenvalues property of eigenvalues. So eigenvalues are going to be, or lie means lie mean to say, if you find, suppose alpha is an eigenvalue of this unitary matrix, if you do the absolute value of it, if you find the absolute value, it is going to be 1. So any for any eigenvalues. So this is one property here.
Sir, A star equal to identity, right? Matrix
A star
into
A
A.
equal to I.
You have written Z, sir.
No, not this is I.
Oh, it's looking like Z.
Yes. Yeah, it's look like that. This is I. Sorry.
Yeah.
So this I means identity matrix. So if eigenvalues are going to be, this case, if eigenvalue, if alpha is an eigenvalue, then this will surely happen. And the next is unitary matrix have, it have also the property is that their columns going to be orthonormal. Columns are going to be orthonormal to each other. And suppose this is V1, C1, C2, C3. I'm not talking about the eigenvalues. I'm saying just columns of that unitary matrix. Those are going to be orthonormal. Okay. How many columns should we get? They're all going to be orthonormal. And regarding the eigenvector is, I'm not sure about the eigenvector. They are going to be orthogonal or not. But one thing is there, it is also always going to be diagonalizable. It is always going to be diagonalizable.
So
Okay.
can you explain first property again?
This one.
First.
So here, suppose alpha. Let's say I have unitary matrix. Okay, by A minus lambda I got the eigenvalue. Okay, some lambda, lambda 1, lambda 2, lambda 3 I got eigenvalues. So if these are the eigenvalues I have, if I will do modulus value, because it may be okay. So eigenvalues are not going to be real. It could be complex also. But if you find the modulus value of this eigenvalue, hope you know how to find the modulus of a, for a complex number, it will going to be 1. This is also going to be 1. This is also going to be 1. So means modulus of each eigenvalue is going to be 1. This is the property.
So using modulus, we just change the sign of.
We change the.
I mean, using the modulus, if we want to find the modulus of lambda1, then if the eigenvalue is negative, it will turn to positive.
No, here not modulus means
Like,
okay. So modulus of a complex number. Okay, so you mean wrongly. So I mean to say modulus here means if suppose lambda1 is equal to x1 plus I y1. So lambda modulus of it is going to be root of. So there is no sign in there is no negative complex number, positive complex number. This is the mean here. Modulus means in the complex is that this one.
that will be, I think, norm, right? Is it correct to say?
So don't say the norm, just say the modulus.
Modulus, okay.
Absolute modulus are absolute value of a complex number.
Okay.
Norm is will come when it will be form a space over a real number, or even the C over C or C over R. Means will form a vector space over real number. That is totally different. Here reading or studying the complex number is not studying the vector space, and complex number have some specific thing like modulus, argument, and some other thing is there, argument, modulus, and something other words are there. So as you are used to study real numbers, absolute value also there, but here the absolute value is meaning differently. So these are the property of unitary matrix. And next is diagonalizability. So diagonalizability is finding the eigenvalue. All other property we are discussing, even the eigenvalues, eigenvector. So if you have a matrix which is suppose you have a 3x3 matrix. Okay, in simple word, if you have a 3x3 matrix, and if you are able to find 3 independent eigenvector, anyhow the eigenvalues are going to be same or not, it's totally independent of that. If eigenvalues are going to be same, even you are able to get 3 independent eigenvectors. Okay, so it's totally independent of eigenvalues, means eigenvalues are going to be same or different, it doesn't matter. Here only the matters that you are able to get 3 independent eigenvector. If you are able to get, then you are able to form your P matrix. Then you are able to form your P matrix, and then using this P matrix, suppose this matrix is A, then you can write A as a P D P inverse, or maybe vice versa. Here would be, you can check which one is correctly here. Generally it is the true one, not true one, it is generally used. So here P is what? P is the matrix. You are writing columns of P as V1, V2, V3. That's the only thing. If you are not able to get 3, suppose by chance you are not able to get all 3, then matrix is not diagonalizable. That's all. In one word, that is the meaning of diagonalizability. If you are able to get 3 independent, you are done. If not, then no. Okay, and this D is here eigenvalues. Lambda 1, lambda 2, lambda 3 on diagonal. Rest all is going to be 0. Okay, so again in another example, suppose your matrix is 5 cross 5
Could you
cross 5.
repeat it again?
Yeah, suppose for example your matrix is 5 cross 5, then so anyhow if it is eigenvalues are going to be same or all are different, or two of them are same, two of them same, and rest one is different, means independent of same meaning. Means either they are same or different, it doesn't matter, but anyhow you are able to find five independent eigen vector. I hope you know how to calculate. So if you know how to calculate eigenvector, in that case, if you are able to find five independent eigenvector, okay, then these eigenvectors surely we will use to find matrix P, where matrix P is nothing but you will write the column of matrix P as a eigenvector. That is your matrix P, and you are able to write your this B matrix as PD P inverse. Clear?
Yes, sir.
Means regardless of eigenvalues, they are going to be same or different, it doesn't matter. Hope you know how to find eigenvectors. If you are able to calculate five independent eigenvector, then just form P and write this form. That is called diagonalizability. If you are not able to find five, directly say that matrix is not diagonalizable. That is the only thing. So that's why here this is the basic proof. Even the proof is there. Spectral theorem means same. This Hermitian matrix is I will always diagonalizable. Unity matrix is always diagonalizable. Some other specific matrix are there. All are, most of them are diagonalizable. So those are some theorems it have that could be proof also. But for the general matrix, this is the only way to say a matrix is diagonalizable or not. Okay, so this is the diagonalizability. So this is we studied these all this diagonalizability. Why we are studying? To get the power matrix. Means, for example, suppose I want to find b square of this matrix, then sometimes it could be easily calculated. Okay? We can calculate even manually. Okay, so but the case is that I want to calculate p power 100. So if I will give, we are not able to do manually, even I will give to computer, okay, the computer will take also time. And even if your matrix B is of 1000, okay, or 100 or 1000 order, then the matrix, then the computer will also be, will give some error, maybe will take longer time. You are not able to calculate also. So to deal with such problem, okay, because you are studying data analysis here, so many times, right, the properties, we have some list of properties for a product, and you want to do you want to analyze that. You will convert that properties in matrix form. You will do something, I don't know, whatever the next ahead thing. As you know, once you do MLT, you will see you so many algorithms there using this matrix, based on the matrix. Mostly most of the algorithms will run on the linear algebra property, or proved by the linear algebra property, so that you are able to get, or you are able to get the correct algorithm or correct way of to get the solution of problem. So here this will misbehave. So in this case we'll use this diagonalization. This could be easily done. By this way you can get the matrix multiplication easily. So here if you do b square, then that means here p d p inverse. This is the b over b, and again p d p inverse. Just writing to be b cross p. And this is p d p inverse, and then p here, and then d, and then p. So matrix actually use the property associativity. Means I can take these two first. And if you take these two first, it become identity. Now p, d, identity, d, and then again p, your inverse. And now this, if you take this association, then it will be d square and p inverse. So doing this b square is doing like this. Doing b power 100 means this is going to be t power 100 p inverse. So that's the use of, this is one use of diagonalizability. There are lots of use you will see later, but this is one use. Now we are doing on, here square matrix n cross n. But what is the case when our matrix is not a square? It is a kind of rectangular. Even we have to deal with this rectangular matrix. How we can deal with this? So there, for this one, the SVD, singular value decomposition, is another form of another simplified form. Means writing this matrix in the some simpler form, like as here. Any square matrix we are writing this one here, any matrix we are writing in simpler form here. So similarly for rectangular matrix, order is not same here. We have to do something. So that is here for a single value decomposition. Means we are writing, if it is m cross n, then you will get a matrix q1, and then sigma, and here is q2, and I think here is a transpose, something is there. You can confirm that. Is this correct? Transpose?
Yes, sir, there is transpose.
Okay. So this sigma is going to be of the same order, m cross n. This is going to be m cross m, and this is going to be n cross n. Okay, so now see it. This is going to be an orthogonal matrix. Now we are here on a real number. Okay, this matrix on, at least we are here, we are doing, even we can extend on the complex also, but for this course at least let's do for only real. So this matrix is q1 is going to be orthogonal, q2 is also going to be orthogonal. As the reason say that this is a square matrix here. Not reason means square matrix. We are doing some simplification here. This rectangular now we simplified here to a kind of orthogonal, and square matrix here is square matrix, and this is this is going to be a kind of simplified form, sigma 1, sigma 2, till square it would be a sigma kind of, and then rest all it would going to be 0 in place of other entries going to be 0, where sigma is going to be nothing but the root of eigenvalues. So means anyhow we are getting some simplified form, that is your CSVD, singular value decomposition. Okay, so this singular value decomposition is an algorithm. I'm not going to repeat it how
Sir?
to do it. Yes.
What would be the size of this diagonal matrix of eigenvalues?
Here, this one.
Yes, the inner part.
This
You said that it'll be 0 and then there'll be a diagonal inside the m cross n. So I'm asking what would be the size of the inner
uh inner part is going to
sigma
be
1,
the
sigma 2
size
is
of
there.
so that is going to be in the process you can check how it is. We are, if suppose this matrix is A, then first we'll find A transpose, right? Yeah, in the process. And in that case it is going to be A m cross m, then A transpose is going to be n cross m, then it is going, finally it is going to be m cross m. So this order is going to be, that is what using that we'll find the eigenvalues, right? Eigenvalues. And even order is, I'm not sure what is going to be the inner part order. I'm not sure what is going to be, but yeah, this order is going to be m cross m.
Okay, sir. Yeah, okay, sir.
This inner part is, I'm not sure what is going to, while doing, if you do the, if you see the whole procedure, you will get that idea what is going to be order.
Okay, sir. I'll
So
have a
I'm
look.
not going, yeah, I'm not going to here discuss the whole procedure. I just giving an idea why we are doing. Okay, the procedure is, you can check that we have to find some transpose, multiplying transpose, and then have to find the eigenvalues, and then uh, after finding the eigenvalues, we have to find the sigma, which is nothing but the root of it, and then next is eigenvector, that q1 is formed by eigenvector of A transpose. Q1 is formed by the eigenvector of, I think, oh no, sorry, yes, Q1 or maybe Q2, and then Q2 is formed by, A transpose A. Either it could be transpose, but we'll get by this way, or or differently also. No, or differently is that there is one formula to find that using the eigenvector of it, multiplying what is that, sigma time or something, some formula is there, right? Anyone can tell? We can see the procedure, that is explicit procedure is there, and we have did a solve with us to find the whole thing. What is that formula to find q2, or sorry, we'll get q2 first, and then q1 will get here, q1 will get here by the formula. What is that formula? Anyone have remember that?
Sigma I,
Yeah, sigma I,
yi equal to
oh, sigma I y equal to, okay,
xi, axi,
equal to xi,
axi, any matrix
axi, yes,
A.
a time, yeah,
Yeah,
axi, yes.
yeah.
Means yeah, finally yi is equal to 1 upon sigma
Sigma
I
I
ax.
equal to ax. Sorry, ax.
Yeah, so this is the procedure. I hope now you have prepared with, because quiz 2 is coming, so this is an algorithm to do this, but I am just telling you why it is so, why this SVD came, at least use, this is the reason why we are doing this SVD. Because we cannot even know, when we have 2 hours, within that we have to discuss all. So this is the SVD. Why we need SVD is because of this reason. We are trying to get single. There is one also, Su's theorem or Sur theorem is there. That Sur theorem is used for triangularization. Means for any matrix. This is for any matrix, but it should be, triangularization means it should be n cross n. It's a square matrix. Triangularization will do. N cross n, it have matrix is n cross n. It doesn't matter anything. Either it could be Hermitian or maybe symmetric or any. It doesn't matter. Not specifying any specific type of matrix. Any matrix is always triangularizable. Means we are able to write in upper triangular matrix. As here, diagonalizability, we used to check there either it is diagonalizable or not. But here in doing this triangulation, we are not going to check it is going to be triangle, we are able to write in upper triangular matrix or not. Just do that. If you follow the procedure, also this algorithm tells you, Su's theorem give the guarantee that any matrix is, we are able to get a convert to a upper triangular matrix. And what is the procedure? Very similar procedure will do, some A transpose A, some things there. You can check what is exactly procedure. But triangularization is for any matrix. We are not going to check first it is able to write in upper triangular or not. Just do the procedure, and the matrix is going to be converted in upper triangular matrix. And also that why we are converting this is because to get a simpler form. Suppose sometimes we are not able to do Diagonalization, just do the upper, just convert in the upper triangular matrix, because multiplying them is again going to be a bit simpler in compare of the original one. Upper triangular, you will get some entries as a 0, and then doing the multiplication is going to be bit easier one in compare of the original one. So that's why the upper triangularization is there, or triangularization. And next is PCA. Till here, anyone have any doubt? BDM session is going on. Yeah, it is recorded. I don't know, but this our timing is usual timing, no? It doesn't clash with other. This is a fixed one. Okay, let's move to the PCA. PCA is positive definiteness is Riemann. Let's do first.
Sir, it's in week 7, I guess.
Yeah. Yeah, PCA is on week 7. So let's do first PCA, then positiveness. We'll check positive definiteness. So PCA is again it is an algorithm. So to get the whole algorithm, I will suggest you please go through with solve with us assignment of week 7. Within one problem, you can understand the whole procedure. And there I have discussed 2 problem in the solve with us. So to understand the procedure, that this is just an algorithm, and if you why we are doing this algorithm is I have discussed with both PCSS, and I have taken and I have discussed why this PCA needed and how to do PCA. In the solve with the session, I have discussed 2 problem to how to do this, how we'll do the PCA. So PCA is principal component analysis. This is algorithm to to change uh, data. So mean to say, uh, so what we are doing here, PCA is an algorithm which will reduce the dimensity of of the data whatever you have given. I mean to say, suppose you have suppose for example I'm saying, suppose you have 3 data. Okay, you have some data you have, let's say this x1, x2 and x3. Okay, suppose you have 3 data here, and this could be this could be in 3 dimension, maybe all are going to be independent. This could be in 3 dimension. Here I said in that PCA session, why we are doing this PCA algorithm is that suppose suppose here is x1 and here is x2 and here is x3, and I want to study this property of this all 3. So suppose you have a very large data till xn you have very large, and it's going to be very larger and larger. In that case, studying the whole data is going to be tough. But anyhow, if we convert this data on only one single data, For example, I'm saying means we can get a approximated data of each one. X2 prime here is X3 prime. Means see this data is from one dimensional. Okay, means this one is going to be one dimensional line, right? This tells you a line if passing through 0 means it is going to be one dimensional. So anyhow, what here, this is the proxy here. Means I am means projection. Proxy means projection. I am projecting here. X2 I am projecting here. X3 projecting here. Means means here what? Uh, uh, Previously I was started studying here and here this one independently, but now I can study only if I study X1 even, because X2 is just on depend on here on the same line, it is line. Means approximate data I'm getting X2 and X3. Means what, I'm converting this three are actually independent, but anyhow I am converting this all three data in one dimensional. So previously it was in three dimensional, but now I am converting in one dimensional. Yeah, when I'm converting it, I'm getting some error here. I'm getting some, I may get error. Surely I will get, not me, I will get some error. That's fine. But so PCA is what we will do. It will actually reduce the dimensity of the data, okay, and with the less error. So less error means first thing it will give even the on which line, even so many lines, okay, so many lines. Maybe you can project here this one all here. Is all three here. Maybe you can project here. But when you are projecting this all three, okay, so which one give the less error while projecting? Suppose now I'm using this one here, X1 here, X2 here, X3 here, this one, this X2n. Okay, so whatever I'm using this one, but if suppose this line is the best line, okay, so this error is going to be, this projection error is going to be lesser. So how I can get that line exactly? Means this line means this vector, right? Suppose this is the vector here. I hope you can match with. If you are not able to match a vector, suppose a vector I'm writing 1 2 a vector. So if you write in R2, what is going to be here is 1 2 means this one. This is 1 2. So means you can think this 1 2 as a line. You can think as a line, whole line. So that means this line is I am representing by this vector. So if I'm saying this is the best fit line giving the very less error, okay, this is giving the less error. So that means what, I am projecting this all three independent data on single, not single, I'm reducing on this only one dimensional space. All of you are getting what I mean to say. No, yes, no.
So take an example that will be good.
Okay.
Yes, so an example will be better.
Okay, let's say I'm taking 1 2 3. Another one is 3 4, not even, -1 0 1, and another one is 1 1 1. Okay, so if you check this, all three are going to be independent. Surely it will be independent. Okay, all three are going to be independent here. So this suppose this is the data x1 x2 x3. Okay, all are going to be independent. Okay, but okay, I am actually projecting this all three data. Okay, projection, you know the projection. I am projecting all this data. So means here I am projecting x1 on, let's say, 1 0 1, x2 also on 1 0 1, x3 is also on 1 0 1. Means all three x1 x2 and x3 I am projecting on this single vector, this one. Okay, on here I'm all three I'm projecting here. Projection, that is the simple projection I'm doing. This is the, I'm projecting all three on here. So now this after projection, let's say all I'm projecting here, I'm getting x1 prime, here is x2 prime, here is x3 prime. After projecting on the single here I'm getting this one. This is the way, right? This is the projection. You know how to do the projection. If you are, suppose this is a v, if you are projecting here, means what is the process to project? Projecting here x1 on v means what is the formula? Formula is that inner product between x1 and v, okay, and outside v divided by norm of v. You know the formula. This is what the projection. This is what the projection. So maybe I'm I'm telling you different from the lecture, so maybe all of you get confused. Okay, so let me back to on the lecture. Otherwise, I am saying in the PCA, what is happening in PCA means I am projecting the all three data on a single vector, okay, and I am assuming all three on by this x1, x2, x3, okay. So when I'm projecting and I'm getting x1 prime, x2 prime, x3 prime, so I'm getting some error. So how I can reduce that error, okay, and also there is a word of maximum variance is there also. Maximum variance is also, you already studied the stat 2, so you know what is a variance and what is the use of variance is I already told in PCA lecture. I don't want to repeat it again because yeah, let's be on the lecture, and otherwise how I can tell. So what is the final thing is PCA algorithm is that whenever you will do a reconstruction, okay, reconstruction of the data means you will project somewhere, okay, on a single dimensional vector space, okay, how I can get the minimum error in the data, whatever you will get here x1, x2, x3, okay. If you calculate the error, which is x3 minus x3 prime minus x3, x2 prime minus x2, x1 prime minus x1, this is the error. How I can reduce this error means how, not even how I will get the minimum error. The PC algorithm actually tells you where you will project so that you will get the minimum error and also the maximum variance. So the question would be, just a second. Okay, so the question would be like this. How the question would be? Question is some data would be given, okay. Simply some data would be given and asked that project this data using the PCA. Using the PCA, project this data on one dimensional, okay, generally the one dimensional space. Project this data on one dimensional space, okay. And once you project this data on one dimensional space, calculate the or find the minimum reconstruction error. And you know what is the minimum reconstruction error? Sorry, no, oh yeah, find the minimum reconstruction error and what is going to be the maximum variance. Find the maximum variance. And you know what is the maximum variance? Maximum variance is nothing but the maximum eigenvalue. So at least within one single NAT type question, it could be asked. Suppose you have some data, find the maximum variance of the data. So what you will do, you just find the matrix using this data, okay, and you will find the eigenvalue of it. And the given the eigenvalues, you will choose the maximum eigenvalue. That is going to be your maximum variance. And so options could be asked on the option type question, how the PC would be asked. One is that one option is going to be, is PCA, once you do the PCA on the data, it will give the minimum variance. This is going to be one option. Second option, it will give the maximum variance. Second option. Third option, the reconstruction error will be the maximum, means or it have the, or a reconstruction error is going to be minimum. This two only, the PCA does two works. What is that? One is that minimizes the reconstruction error. Second one is the give the maximum variance in the data. These two works do the PCA. So it's depend on. So the question is, if you do, I will suggest you again. If you check the old question paper, you will get what kind of question asked in the PCA. Very similar type of problem would be asked in this quiz also. Not going to be changed even. What is PCA? PCA is just an algorithm. On the PCA, we are not able to create different problem also. It could be repetitive, or it could be small change in your data and asked. So if you do older question paper, you can easily do the PCA problem. Now next is positive definiteness. So here is what is the positive definite means. We all focus on only the matrix. A matrix is going to be positive definite or not. It is based when we'll say a matrix is positive definite. Again, here the role of eigenvalue is eigenvector. In PCA also the role of eigenvalue eigenvector. Previously also diagonalizability or other property we have seen the eigenvalues eigenvector, eigenvalues eigenvector. So in this the quiz to whole question, as you can say, you can visit on the eigenvalue eigenvector. If you are able to calculate correctly eigenvalue eigenvector, half of the QP you are able to do. You have to at least know where I will use the eigenvalues eigenvector. So positive definiteness also, just calculate the eigenvalue. If all are positive, then it is a positive definite. If one of them is positive and also 0 is there, semi-positive definite. Negative plus 0, semi-negative definite. Semi-negative. If all are negative, then negative definite. That's all the positive definiteness and negative definiteness. And also there is another type of problem would be there. What is the next one is that you have it would be written like x square plus 2xy plus y square. What find if I am writing this one as a x a what is that writing to be? Anyone can tell what is
X
x
transpose.
x transpose, because it is a scalar, no? So yeah, x transpose ax.
Yes.
What is going to be our a here? So a is a is, if a is going to be, if it is writing like this, ax square plus
It is 1 1 1 1.
Here is 1 1 1 1. So here is writing to be ax square, and this is here a b xy 2 times, plus here is by square. If you can compare with this, and then our a is going to be ab. Sorry, here is c. Sorry, here is just b if you're writing to b, and here is c. Here is c. So here is b, and then c is here. Means here, if you see that this is going to be a symmetric matrix. Yes, you can compare. We can compare with this and here, and writing to be a. If it is in higher and 3 variable, then if you do one practice, you will able to write the matrix A there. It is of ax square plus by square plus cz square plus 2 something is some 2 times some xy, then plus 2 time yz plus 2 time xz, and some coefficients are also there, you can check. Then it will be converted at a b c, something is there, you can check with that. Generally in 2 variable would be asked, but I will suggest you check with the 3 also. These are just a formula. If you do the practice easily, can even if you do 1 or 2 problem before the 1 day exam. Why I'm saying at least these topics we just cover, okay? Just do one problem, at least one problem before the exam, going to be before the exam. Whatever I am telling here, that much problem you did at least your own way, at least once by own. Then you are, I will not guarantee, will say, but you will surely get mark above 75 at least. But yeah, at least do yourself this type of once. Just do one practice, you will remember itself, and then you can easily do in the exam. So this is the definiteness, positive definiteness, and surely asked to be if A is going to be positive definite, negative definite. It's depend on the eigenvalue, you can say, as this is the list of. And last one is, last week is unconstrained optimization problem. There is just so what is the way? So unconstrained optimization is going to be, the problems are going to be either of a single variable or double variable. Okay, so it could be of, maybe of asked problem would be, find the maximum value of the function. But even in the 2 variable case, simply I don't know what is the context type problem, I'm not able to create till now here, but it could be given the 2 variable function, okay? And let's say, for example, 3x square plus 2y plus 3xy, or let's say minus 3xy, and I want to find the maximum value of the function. The process is, so here is, this is an unconstrained optimization. If it's the constrained optimization, then surely another function g, okay, surely another function g would be given, okay? And not only g, surely some relation would be given, either it is going to be less than 1 or greater than 1, means surely another relation, some relation would be given, maybe less than or equal to, greater or equal to, some relation would be given. It tells you that I want to optimize this function on this constraint. So this is called constraint optimization. This you will see week 9, but here we are only on constraint optimization, so surely this could not be there. So if it is unconstrained, means no, this one is not there. So just need to find the optimum value of the function, either the maxima or minima. So the process is to get this maxima minima. Already we are studying maths to find the partial derivative, which is nothing but 6x plus, this is minus 3y, and with respect to y, it is going to be 2 minus 3x, and both will equal to 0. This will give x is equal to 3 by 2, no, 2 by 3. And from here we can calculate, if you have 2 by 3, means here this is going to be 2 by 3 into 6 minus 3y equal to 0. 3, 2, 4, and this by this way, y is equal to going to be 4/3. So using this, I got this y value. So point is going to be 2/3 and 4/3. This is the only critical point. These are the whatever the point you will get, that is called critical point. And once we will get critical points, then fx will find the double derivative, and then this, sorry, if Hessians, what is the Hessian? Hessian is determinant of the Hessian. This is the Hessian matrix. So yeah, yes, this is xy square minus. So here is f of xx of yy minus f of xy square. This should be positive. If you calculate this should be positive. Then it's depend on if it is positive, minima, negative, maxima. This is what. Let me check once. This is what in this week or something more. Okay, so here is this is unconstrained. So this all is actually suggesting the to do an algorithm. So by getting this way are going to be by the gradient descent algorithm. So that is the sir is actually creating a base. How we'll get that by an algorithm. So we know the method by the critical point, but we are next in the next upcoming MLP will usually we are doing data analysis on the computer. So we have to create each time we are not able to by this critical point, we have to find a proper algorithm. So yeah, one problem surely I will suggest you, please, you can expect one problem on gradient descent. And what is a gradient descent algorithm? For the gradient descent algorithm, we need some initialization, initial point, some step, what are the steps we are taking, and then one algorithm, and that algorithm is writing to be this here, x t plus 1 iteration. T is iteration, initial point, and some rate would be given, and we'll multiply with the gradient. So
Sir, any question on Taylor series?
on Taylor is very less chance to come. But yeah, at least you should to know how to expand or maybe writing a Taylor series of a function for a function. So for example, at least you should to know, for example, let's say I'm giving an one variable case. Okay, so let's say x to the power 10, or maybe log function. Let fx is equal to log function. Find the Taylor series of this. What is the Taylor series of this around, or maybe around means at x is equal to 1. So So how we'll get this Taylor series of this function? So what is the way? Taylor series is nothing but value of the function at 1, then derivate value at 1, x minus 1 square, sorry 1, and then double derivative x minus 1 factorial 2, triple derivative at 1 value x minus 1 factorial 3. This is the Taylor series. Means each time you have to derivate, find that value, and writing like this. So at least you should to know what is a Taylor series. That is going to be enough. So that if maybe one problem asked in the option wise that which one representing the Taylor series at some particular point, you're able to calculate easily. And this Taylor series is very easy, just doing the derivating it and finding the derivative at that point and writing like a series.
Sir,
Yes.
sir, could you take one question on Taylor series?
So that
Yes,
is
sir,
what
please.
May I
so
mean,
this is so that this is what I wrote here. Let's say function is this one. Let's say, so problem if it is asked, so it would be on the one variable mostly. So suppose if I have function log x, I want to find the Taylor series at 1. So what is going to be? So Taylor series is, let's find derivate first, which is going to be 1 by x. Okay, double derivative. So each time let's find double derivative. This is going to be minus 1 by x square. Triple derivative is going to be minus 1 by, oh, not even minus, plus is going to be, and then 1 by 2, not 2. I mean, see, this is going to be what? Minus x square. Minus x square to minus 2. So this is minus 2. And
So plus
minus
2
minus become plus. Plus, so 2 times 1
2 by
upon
x cube.
x cube.
x
2 by
cube.
x cube.
So now, so this is going to be f1 is going to be 1 by 1. And f2 is going to be, sorry, double derivative at 1 is going to be minus 1. F triple derivative at 1 is going to be minus 2. So by this way we'll calculate here. Then what is
So
minus
2,
2?
only 2,
Yes, only
not
2.
minus
It's just 2 here.
2.
So then now till here it is there, maybe you can calculate, it depends on the option, how many terms it is asking the option, you can calculate that much. Then fx is going to be function value. So function value at 1 is going to be 0. Log 1 is 0. So 0 plus derivate value at 1 is going to be 1 x minus 1 plus double derivative at 1. Double derivative at 1 is minus 1 x minus 1. So here is a square. Here is cube. Square upon factorial 2. Factorial 2 is just 2. Then triple derivative at 2 is 2. X minus 1 cube. Upon factorial 3 is 6. And that's the thing. We'll proceed here. This one.
Denominator will be a factorial.
Huh.
Okay.
So this is a easier way to remember. This is the factorial series. So how sir is writing here? So he's writing in the eta and d square form, and d square is what is the increment here. So what is here sir is writing? Let me match with the sir. What is sir is writing? So and let me mute to.
Hello, sir. Hello.
So what is here is happening, this eta anti, let me explain is what is here. So this eta is, and this eta is, this is a small increment, or what is here, or this is nothing but, this x bar is, or let me match with our one. What is here? This is the derivative one. See that this is the derivative here we are writing. And d and eta is t is this part. No, I think I just. So here is the whole thing is, writing to be x as, if you write x as, what is happening here? This is, sir is actually managing it here. Writing to be, this, there's a different Taylor series means here writing to be x minus a. So here is this a is, our case is eta d. Eta d. If this means that this x is our value here. This is written where I am writing the Taylor series. If you, as our case here, so let me the same match with the whatever I just wrote. So this x is our this one at 1 here, the derivative each time sir is writing, and this x minus a is that small increment, and eta is that this x minus 1, that this d is an increment, and d is a kind of, d is actually increment, this x minus a, that where I am writing this, that is d is an increment, and this eta is just a scalar multiplied scalar for our sir is writing the step, that in gradient descent algorithm, what is there, xt plus 1 is the initial plus eta and gradient of the function with the initial t, with the initial or whatever the t is there. So that is step. So this is what the rate, at which rate it is. So this is the rate here. This is the rate. But here is, I don't think sir is not writing here in this fashion. So I don't think the Taylor is asked. There is chance to come. First thing is that because sir is not wrote in the proper Taylor form as I am wrote here. I just given, I'm from my side. I don't know. I given here now. So Taylor series is this another. This is the another form of the Taylor series. But it's depend on the properly. It will mention what is your eta, what is your t, and where it is, where I am writing the Taylor series. So properly Taylor series writing to be is, the question would be asked like this. But now I am not saying to ask because that is given differently. In the mathematics, generally the Taylor series asked like this. But here,
There are questions
where in the Taylor series in GA
from the Taylor series and in the PYQ. So if you could take just one question, should I?
Are there
Yes,
enough
what is that
questions
from?
asked in the PYQ? Sir?
Very less chance. I don't think.
Very less.
It
I
is
think
asked, what is
most
that
of you have
problem?
seen the gradient
It
descent
says,
questions.
so it says f of 1 to 3 equal to 10
F
and
of 1, 2, 3 is equal to
3
10.
equals 10 and nabla
Hmm.
f of 1 to 3 is 157.
1, 2, 3 is equal to?
157.
Okay. Okay.
And then find the value of f of 2 to 2.
F of 2 to 2.
Yes, sir. And the answer given is 4.
What is answer?
Using the first order Taylor series, they said.
Using the
Expansion.
first iteration, no?
Yeah, first order Taylor series expansion.
A first order Taylor series. Okay, first order Taylor series expansion. Find the value of this.
Yes, sir.
So here is F222 or F1222. What is that?
No, sir. They have they said find the value of f of 2 to 2 transpose, and that is the using
Transpose.
yeah, I mean the vectors will be transposed.
Okay,
I
okay,
mean,
okay.
if they have written in this fashion, then it will be yes.
Okay, this is a vector. Oh, so you said a value. So this is a vector. 1, 2. Sorry, this is a vector. 1, 2, 3.
Yes, transpose
Okay. Transpose.
is 10,
Okay.
and then the nabla f of 1 to 3 is 157 vector.
1, 5. Okay, this vector one. This vector. What is here vector?
It's 10, 10. No, that's not a vector. That's a value
This
of
is
10.
going to be scalar.
Yeah,
Okay, and this is 157. This is going to be scalar. Sorry, this is a vector
vector. Yes.
transpose. And what is going to be this one?
2 to 2. Yes. They said find the value of 2 to 2, f of 2 to 2 using the first order Taylor expansion. That is a question.
Okay.
And the answer given is 4, but the making portion is doubtful, sir.
What is going to be this? Okay. So here is so this is a multivariable case. So this is a multivariable Taylor series, higher Taylor series and higher dimension. Where is that formula exactly? A Taylor in higher order Taylor series. This is what it is. Okay, vector, scalar. Let's do on here itself. So in a higher order Taylor series, what? So this is the, what is the in higher order? If suppose f of x, y, z is given, means here this is the form, and some function is given. So what is that? The function value at there, x, y, z, and then what is that?
Nabla D transpose. Sorry.
Gradient, yeah.
Transpose nabla. Eta.
Gradient of f. Yeah. So here let me write it. So here is gradient of, okay, gradient of at x, y, z, okay, and the dot product with, so here is, if it is a written dot product, if it is I'm writing, so here sir is not mentioned the dot, so in the same sir order it would be, what, so this is, so what is you are saying, eta d, what is that?
Yes, sir. Eta D transpose nabla
Nebula
if
of one x, y, z.
x, y, z.
Let's So this is the first order Taylor series. Okay. So
In the lecture, I have said that this D is minus nabla of F X Y Z.
this T is
D D is minus nabla of F X Y Z.
yes. Oh no, this is what it is. Okay. Now let me write for our case. Let me for my case at least, then it will be more clear as. So this is plus, and next is
So, sir, LHS F of it will not be X Y Z. It will be different value. The new coordinate.
this is going to be the left hand side. This
Yes,
one.
yes.
This is not going to be XYZ. This is going to be here for our case 2, 2, 2 is there. This is going to be the value at the at 1, 2, 3 transpose, and this is part we want to know. So here is going to be 1, 2, 3 transpose, and here is what this is. So let me write the my case first. So what is the Taylor series or first linear approximation in one variable? It is called one Taylor first order Taylor series. So that is called dot product with the gradient of f with x whatever the x minus a, y minus b, z minus c. So what is here? So here is this is the increment part. This is the increment part here. So and this is the these two are dot product written. What is eta here? Why sir is mentioning eta?
Eta is steps, sir.
Step. So what is the step? So here, what is the step in this form?
Nothing.
Here in this.
And the question, there is nothing.
That is what eta is step, but here it is not mentioned in this problem. Okay. So what is the gradient descent? And generally, sorry, not gradient. That Taylor in the Taylor series is in the multivariable case. This is I want to find the gradient. Okay, generally in mathematics, what is that? I will tell you that what is eta. I don't know. This is going to be with the mix of these two. So we'll see it. But in the multivariable in mathematics generally, what is that Taylor series in three variable is? I want to find the Taylor series of this one around or at point 1, 2, let's say for at point A, B, C, general case, then Taylor series of this one is going to be function value at A, B, C. Okay. Then next is gradient of the function at A, B, C dot product with x minus A, x minus B, and x minus C. This is what the first order Taylor series. So if you do this here,
y minus b and z minus c.
Y minus a, b, and z minus c.
sorry, this is y minus b, and this is z minus b. This is what the Taylor series is in the multivariable case. So this is exactly the same. This dot product is nothing but the what? This dot product is the transpose of writing to a increment. So finally, so this eta is this eta d is mixed with one increment. Okay, the increment. That's why this eta is a step. So here iteration is first. So here eta is not mentioned. The step is there. So that means the first in the first iteration it said no, so eta is 1. Okay, so eta is going to be 1 here, and then this d is going to be what? D is going to be 2 2 2 minus 1 2 3, which is the vector what? 1 0 2. This is the vector going to be. So dot product
0 minus 1.
Okay, see, this
1,
is
0
1
minus 1, sir.
1 0, yeah, minus
Last one is minus 1.
so then this is going to be the vector is going to be this. So finally this is 1 0 minus 1, and the gradient is given first 1 5 7, and if you do dot product at here, so this is going to be at 1 2 3. This is the here. So finally we can calculate.
Are you getting my
Sorry?
question?
Sir, the definition of in the lecture D equal D is, they said, is nabla of, I mean the minus nabla of F at the point that we know the value of.
Let me check it.
So how is it?
Yeah, so let me check it. Where is that D? No, this is not D or D times nil. No, this is not your D.
Note thing, sir.
Not if D is this one. If your D is this one.
So what is the situation, sir?
So this is the sir is telling you the theory. If D is this one, in that case, this part is going to be just your modulus of. So what is the next one? Let me see if the next is. I mean, this part is going to be negative. So he's actually resulting something. He's actually resulting something. Otherwise, D is generally your increment. D part is your increment. So I don't know, sir is not mentioning here, but D is your this part only. Okay, whatever I am writing here. D is your increment. Eta D is a step number of steps, I think. So here is eta is I'm missing something. Let me play it. What is eta first? D is your increment, I'm sure, but what is eta here, sir, is taking? Oh, so this scalar is taking. So this eta d is so increment. So sir is saying at point x plus eta d, that eta d is an increment. So both eta d is in the mixed form, just in notation wise sir is writing here. So I think you are able to listen. I just listen it. So this eta d is your increment. Okay. So here is this eta d here. If I am writing eta d here, so this eta d is, we can take this as this increment. This is what it is.
It's actually the gradient descent form.
Yeah, sir is writing in the gradient descent form, correct. Maintaining the gradient descent form, that's why it is writing. Otherwise, if you listen clearly, that point is writing, sir, x plus eta t the new point where I'm actually evaluating. This is what. So this is our original point, and this is the increment part, whatever you are doing. So our increment part is now here we have calculated. Clear? Is this clear?
Okay, sir. Now it is clear. Yes, sir. Thank you.
So this is what actually in the mathematics, no. So sir is writing here in this part, but in mathematics generally, this is the Taylor in the first order Taylor series, the multivariable. So see it. This is the increment. What is the increment, right? This is the original one, and this is the new one, and this is what increment I am calculating, the vector, increment vector, and multiplying with the where you have calculated the nebula, means gradient, dot product with that. So this is what it is done here.
So, sir, what will be the next term in this sequence? What
So
you
in
have
this
calculated?
so
We
finally
have
just
given.
write the value here. So finally you have calculated, we have calculated at 1, 2, 3.
No, sir. That
And
is okay. I mean, I'm asking the sequence you have given in the mathematical form.
So
So,
in the
Sir, I
next term
just
it is going
मेरे
to
पास एक ही क्वेश्चन है सर, excuse me.
sorry. Please if you mute yourself.
Sorry to disturb me because I just have one question only.
What is your question?
सर जो मॉक रिलीज हुआ है उसमें ऑलरेडी आंसर लिखे हुए हैं.
Is it? I think due date is given now. So that's the thing here. Due date is over, I think.
Sir, due date
I
is
think
given August.
August.
Yes.
That is the past due date. Actually, it is 1st December.
So I think you are
No, but if you
opening.
open, yeah, if you are
that is a
opening
mistake.
showing August, it's already closed.
Yeah, it is a mistake.
So
So
what is
because
that?
this way we cannot claim for the this bonus marks and all this one, sir.
But I don't think bonus is there on the mock. No, I don't think.
Sir, it
Bonus
is
is not there. Is it mentioned bonus on mock?
yes,
Yeah,
sir. They have said it will be considered for the grading.
In grading
Final
document,
grading.
it is rated.
Yeah,
In grading document mentioned.
mentioned.
Okay.
No, sir, not in the grading document. I'm saying from the page.
Okay, from the page. Okay, but if it is not mentioned in grading document, then it won't be. But yeah, it is a bit confusing because if it is not in grading document, then it won't be considered for the bonus mark first.
Sir, it is
Okay.
there.
It is mentioned in the grading document.
Yeah, it is there.
Then
Sir,
the
maybe
theory.
it is
it's just for your information, you can sort this issue after first also, you can continue. And another one more question, yes, sir. You will teach, you will taking doubts for PCA today?
Yeah, I have this now. I have done almost. I have done. So if you have doubt, you can tell me what is your doubt.
Sir, regarding PCA, yeah, regarding PCA, first step is so I have to take out the mean. Second step, we have to take out the covariance. Third step, we have to take out the eigenvector. Then eigenvector we have to take out, right? Then the fourth step, when we have to find the projection, we have to multiply the projection, the whatever the like for example, our matrix given 1, 0. So that is our x1. So we have to take the transpose and multiply with the eigenvector.
Yes.
Sir, why we are multiplying with the eigenvector second time also? We are multiplying eigenvector 2 times. That is my question only.
That is the algorithm. That is what algorithm it is.
It is xi transpose into u1 times u1 plus x2 transpose times u1 into u1 is the eigenvector with the which has the largest eigenvalue that will be taken as the PCA.
That one I know, sir.
Yes.
So to get the projected data.
Okay, so this is because the formula also, like formula mentioned x1 u1, that's it is mentioned, but I am not able to get this part only. That why we are.
So,
And one more question, sir, for normalizing, because generally in this one we are normalizing the eigenvector. Once we get the eigenvector, we have to normalize it.
yes, yes, we have to normalize. We have to normalize.
Correct, sir?
Yes, yes, we have to
So,
normalize first.
yeah. What is the reason for normalizing, sir?
Generally, we changing in the unit kind of changing that whatever the eigenvector we are getting, change in the unit vector. That is what we are doing. So actually, there is no use of we have the scaled kind of eigenvector. There is no use, so that's why generally we do on the unit vector. If you do on unit vector, that is true for even all any scaled vector. So that's why it is even get the simplified form also, and
Okay.
generally we do on unit vector. That's all I will say on the answer, because see, this is an algorithm. No, if it is a theorem, then we can argument, but this is an
Yeah.
algorithm. This is an
No, it's
algorithm.
okay,
Even
sir.
we cannot
No problem,
argue
sir.
with it.
No problem. No. Just asking only,
Hmm.
sir. Thank you so much, sir. And one last thing, sir.
Hmm.
Hello.
Yes, yes, I'm able to hear you. Yes.
Sir. Yeah. When we are 1 minute, sir, I written it somewhere. The eigenvector that we are multiplying, we have to take the larger one only. Correct?
Yes. Yes.
And we are getting, because but we have in this week, and I have seen the PYQ. We have a question regarding the first level projection only is there. So second level will not be there, right?
Probably it is not. So mostly the only one
Thank
level, single one dimensional.
Yeah.
Yes.
No, thank you so much,
Because
sir.
if it is
Because
if it is a more than then for the quiz purpose it is going to be difficult. Not even within the time limit we cannot do.
no problem, sir.
Generally it is one
No,
dimensional.
because for me, because if I'm seeing the formula, I stuck there only. That why we have to multiply 2 times the eigenvector. What I was thinking, maybe because in the your assignment also, like you have taken the class, everything, you just multiply, but I'm not able to get why we are multiplying this 2 times. So so that one is, first we have to take the dot product of the transpose and the eigenvector, then we multiply with the one more time with the eigenvector. Correct, sir?
Yes.
And
Vasudev want to
Thank you
say
so much.
something. Yes,
in the
Vasudev.
last
Thank
we
you.
calculate the reconstruction error also, right?
Yeah, in the
The
last, yeah,
reconstruction
we used
error,
to
no
come.
problem.
To get the
Because that one, once we get the new matrix for the eigenvector with the projection, we just have to minus it from the original vector, then square it, then add everything.
That is, yeah, that is the
Correct?
error. That is the error. Yes, correct.
Correct?
That is the error. Yes. That is the error.
Thank
That
you
is
so
the
much.
reconstruction.
No, because in between only that point is missing.
Okay. Okay. So
Thank you
actually,
so much, sir.
why I'm not the whole algorithm I discussed, because that is just algorithm. That's why I said if you do
No,
one before the exam, if
you
you
have
do at least one
sir,
problem,
you have discussed the algorithm, but only problem is that
yeah.
suddenly you just change something, and from there only, because for that video only, that part I have put 1 hour, 2 hour, but still I'm not able to get it. Even I asked other students, they're sending the formula only.
Yes,
Nobody is telling me
why
they're
it is so?
sending xi, ui. That's it.
Yes.
Xi,
So
ui.
actually,
Everybody
why
sending
many
me
of us
xi,
you are
ui
not able
only.
to answer? The reason is that, see, the second time multiplying the eigenvector with mean is that when your mean is variating, then it will be multiplied. If your mean is even 0, I have seen, if you see the solve with us, no, you will get more clear. I have told you
Yeah,
why it
no
is.
problem, sir. Only this was the issue. No problem. Later on we'll think about it after the exam. Thank you so much,
Yes.
sir.
Yeah. Okay. Fine. Yeah, so that's all the thing also. Almost I have discussed this, even the multivariate also. So don't worry, this n eta d is just an increment. Okay, so in the next step, somebody is asked that what is going to be the next step in the some, suppose if it is in
Yes,
the
the next term, sir, in that
next term, yeah.
sequence.
So in the next term is going to be that is just a second. So the thing is it is going to be
It will be the Hessian, right, sir? Instead of the tabla, it will be the Hessian.
Hessian, yeah. Something is there. Okay, this is just a formula. So even I
I
have to
came
do the
across
Google.
this formula first time, so that's why I'm asking.
Yeah, writing or even where is that? Sir is wrote this t square, no? The again increment and this double derivative. What is in the vector form? Okay. So okay, so just to Google actually.
Sorry to disturb you. One more question is there, sir.
Yes.
Practice assignment.
Okay,
For
just
the
a second.
practice assignment. Yeah.
This is the first order. If you see it here also generally in two variable case. For
Yes.
second order derivative, this is here. So Hessian is or there or in the two, or if you are doing on two order, it is here. So double derivative. So from here it will start double derivative there, and then x minus a square, then xy double derivative with respect to xy, and then x minus a y minus b, and again double derivative with respect to y only, and then y minus b square.
Okay.
Or
Okay.
any intuition if we have to calculate such questions
No,
using
no, 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 no,
because higher dimension itself is complex, which
yeah,
sir has mentioned in the lecture.
no, no, no. So no, so it is not going to be even. Sir is not writing. Then how it could be asked?
Yeah.
Okay, sir. Thank you, sir.
Okay.
Yes. Okay. Yeah. Yeah. Somebody's was. I
Yeah.
think
SVD
practice.
graded week 6 graded assignment question number 11.
Okay. So that's all the in today's session. Let me take this problem. Okay. Which question number?
Last question, sir.
Okay. This one. SVT.
Yes.
Okay. What is it out here?
Sir, I'm not able to sort this one. Because for the 4 by 4, nothing has been. 2 by 2 is okay. 2 by 2 easily. We can take out the Q1, we can take out the Q2. Sigma also there, no problem. But for 4 by 4, I'm not able to sort at all.
Yeah. So that could be, so you have you gone through with the solution?
Sir, I have gone through with the solution. Even for like if thinking like if maybe I am doing some mistakes in this one, I use the metric multiplication using the proper software also. Everything I did, my metrics, everything coming same. But after that one, Q1, Q2, this one, it's not coming correct.
So
If possible for
see,
you, because
one
4
thing
by
is that let
4,
me tell you. See, one thing. Let me tell you, this Q1, Q2 is not unique. Okay, so it may be whatever you are getting, that is fine. But if you check, if you are multiplying, if you are getting correct, okay. Let me tell you the verify thing. Okay, so here verifying thing is that if you just multiply all, if you are getting a left side, then that is correct. And whatever you are getting, okay, so let me tell you, whatever you are doing, and once you do the multiplication of the whole multiplication, if you do all three multiplication here of the matrices, if you are getting correctly a, then you are also correct. So let me tell you that this Q1 and this Q2 is not unique. Okay, for you it may different, here it may different. But the verifying thing is that once you do the whole multiplication, it should be equal to the left side. That is what the verifying thing. Even you can verify yourself.
Sir, what you are telling, sir? Equal to left side means equal to the 1 0,
Means
the 2 by 2, 2 by 4 matrix.
yeah, this should be get this will you once you do multiplication, you should to get this one. If not, then you are doing wrong. That is the answer. That is the verifying way.
So
That is the way you can verify.
multiply this everything. So we don't have to take out the SVD fully for this kind of question. We just multiply all this one, like the 1 0, all the metrics. We multiply everything. We'll get the value of A.
Yeah. That is what here equality written. No? That means if you just multiply this left side equal to this A should be, you will get here. This one you will get here if you just multiply. So this kind of problem if you have, then the best trick is that just do the multiplication. So it's depend on you how much you are very comfort to doing the matrix multiplication. But from your side, whatever you are doing, whatever you are getting, you can verify yourself where I am making the wrongness. If you just do the final multiplication, left side, if you are getting the same as left side, as you are getting the after multiplication, you are getting the same as left one, then you are correct. If not, then you are not.
No, what I am doing, I am getting the SVD. I am taking out the full SVD, the normal procedure SVD, how we take out, I am taking out using that only. So you are telling the one 2 by 4 matrix will be equal to the everything which is written in the SVD. It should be equal to the SVD.
Yeah, that should equal to the left side. Means your original matrix. That should equal to the original matrix. That is what here written. No? This is A equal to this one written. So if you multiply right side the whole matrix, you will get this matrix A. So this is equal to sign you can use for verify.
Yes. Got it, sir. I am doing, I am taking out the full SVD. I am solving the SVD. That's why it's taking time also. Thank you so much, sir.
Yes. Okay. So I hope this is I don't know how much beneficial, but let's see. Maybe on the we'll see it. There would be a revision or not. If it is there, we'll update it in the calendar. And that's all for today's session. Anyone have any doubt? Yes.
Right now there is no revision session again.
Right now, no. So I have to ask to my ops team to be update. I don't know how it would be. I thought it should be there, but I don't know. It would be there or not. I have to check it. But once it will be, it will be updated.
Saturday only, right?
Okay. Yeah.
Thank you.
Yes.
Sir.
Okay. Yeah. Thanks, everyone. Good night. Bye. Best. All the best for the exam. So I from my side, let me tell you. Don't worry for exam. Whatever I am saying, no. Whatever today topics I wrote, at least do one practice on yourself. One practice, even the own graded problem. From your side, just write one problem, and just be proficient doing finding the eigenvalue, eigenvector, and do one problem on PCA, do one problem on SVD, do one problem on definiteness, do one problem on at least gradient descent. If you do at least one problem fully from your side, I'm surely saying you will get at least more than 75 marks. So because the questions are
sorry, in case of SVD, if we had to calculate the full SVD like that question.
So if it is SVD, so just now you can use the trick. Sometimes you don't know, So just now I discussed this trick, right? So you can use this trick sometimes. So if not, then just use trick also to avoid a longer calculation.
Okay.
Because I know you know also the way. I know the way, but sometimes doing all processes be difficult. So use some tricks.
Or even it can be in the sub questions. I mean, one large question.
It could be some, yeah, it could be in some part also. Maybe it could be asked in, in one part it could be asked this one, in one part it could ask this one, in one part it is asking the third in
Q1
between
sigma
sigma part.
Q transpose.
Yeah. So in that case, you have to so it's depend on how the problem is asked. Here the single one in the single option it is asked. Okay, but all the best. Yeah, thanks. Bye bye.
To quiz one, number of questions.
So, sorry, number of questions probably.
16.
Just check with older QP. I will again suggest you at least from your side. So TA session is going on, right? So say to TA session to discuss QP, and also already he is used to discuss also, and the older QP will give more idea, because if you see the trend of the question paper, at least each term you will see the very similar type of problems, only the data have changed, otherwise the same will be there, very small changes usually. So, okay, so the QP will give you the more idea.
Okay, number of questions regarding.
Yes.
Okay.
Okay.